you everyone for attending this week's seminar. It's our pleasure to have a student from McGill. He's Andrzej Pokraka, who works for Simon Caron. And Andrzej is finishing soon, right? So you're finishing your PhD this year?
Yep.
And Simon said soon to be postdoc, so
yes.
Where will...
yeah, I'll be going to Brown.
Okay, perfect. And so today he'll tell us about the duals of Feynman integrals and some mathematical structures hiding in our beloved Feynman diagrams. So Andrzej, the floor is yours.
Well, thank you for giving me this opportunity to share my work. It's all going to be based on these two papers that we put out last year. So the outline of the talk is usual motivation, what kind of problem we're going to tackle, which is integral reduction, discuss a little bit of what sort of the traditional or current practices on how people do this, and then I'll give an overview of our improvements. I'll take you through our algorithm workflow of our algorithm, expand a little bit on some of the key steps, which include building a basis, finding the differential equation satisfied by this basis, and then using the something called the intersection number to compute integral coefficients. And so this is a relatively new technology, at least in the physics literature. So we're still sort of very much in the development phase, and we kind of suck at multivariate intersection numbers right now. So yeah, there's some. I mean, it's okay since we've only been doing this for 3 years, but or 2 years, and we expect it to get better. But yeah, that's sort of the major roadblock right now, and I'll say a few words about that, and then just conclude with some future directions. Okay, so the problem we want to tackle is integral reduction. So essentially, we're thinking about calculating some scattering amplitude, and this could be some very complicated process in QCD, for example, where there's hundreds of or even thousands of Feynman diagrams. And if you were to sort of naively integrate each one of these integrals like brute force, it would sort of it'd be very, very challenging. So what saves the day is actually this ginormous number of integrals is actually spanned by a finite set of basis or master integrals. And moreover, these integrals that we see in a physical theory, they have lots of numerator structure. So it's not just like some simple scalar diagram, which is 1 over propagators. And so we also need to be able to reduce these complicated integrals with numerators into something very simple, like these scalar propagator diagrams here. So at one loop in 4 dimensions, the decomposition looks something like this. We have some rational term, coefficient times a tadpole integral, another coefficient times a bubble integral, all the way up to so the remaining problem is how to find these coefficients. And at least our favorite way, or what we think is a very good way to do this, goes under the name of generalized unitarity, which essentially says, well, let's match the branch cut structure of this side to our ansats here. And a particularly beautiful result is that the bus coefficient is actually obtained by taking the residue on each of these propagators. So I cut each one of these propagators, and when I cut a propagator, the amplitude factorizes into a bunch of tree level amplitudes. So this box, this amplitude, this 4-point amplitude, is factorizing into a bunch of trees, and this coefficient is literally just the product of these trees. So this method is particularly appealing because we're really building up some sort of a complicated 1-loop integral from already understood simpler observables, which are tree level amplitudes. And generalized unitarity also highlights that the analytic structure of Feynman integrals is also determined by its cuts. And the challenges in this procedure of generalized unitarity is that to construct these, like this box coefficient was really easy. It was just a residue on each one of these propagators. But to go into sort of lower topologies, such as finding a residue formula for this tadpole, it's actually quite challenging. There's many subtractions you have to do because the topologies talk to each other. They can all have the same sort of cuts. They share cuts. And it's also much harder when we're not in exactly d equals 4 dimensions, when we're in generic dimensions and we have, you know, 4 minus 2 epsilon, where this epsilon is some generic but small parameter. The goal is to find a systematic formalism for extracting these integral coefficients in any dimension and for all topologies in a way that maintains this spirit of generalized unitarity, where cuts and these residues of cuts are playing a important role. One loop, in generic dimension, or 4 minus 2 epsilon dimensions, the decomposition of a one loop amplitude looks like this instead. You'll notice that we've lost the rational term. The rational term is now, that information is inside the epsilon dependence of these coefficients now. We've gained an additional integral, this pentagon, which does vanish in the 4D limit. And so what we want to find is residue formulas for these coefficients. And as I said before, keep this intuition from unitarity cuts. I want to contrast this with sort of the standard way of doing this, which is using integration by parts identity. And essentially, we're pretty good at doing integration by parts. There's a lot of efficient algorithms out there that will do this for you. So the downside is that it's sort of a black box. We don't really there's no intuition for why cancellations should happen or why there's certain simplifications. And integration by parts also introduces square propagators or cube propagators, depending on what you're doing. And it doesn't, cuts are not necessarily utilized. Right. The question is, oh, sorry, before I say that, let me just do a quick review of integration by parts for those that are unfamiliar. It's really a simple statement. It's just that in dimensional regularization, the total derivative of a total derivative vanishes. So as an example, if I expand out this total derivative here and do some rearranging, I actually get this second line down here. And I see that this one Feynman diagram on the left is equal to a difference of two Feynman diagrams, where the black dot is indicating that this particular propagator has been squared. And to get rid of the square propagator, we have to do another round of integration by parts. So the question is, is there a better alternative to integration by parts to do this in generic dimensions? Well, an answer is to use intersection theory. And this allows us to extract these coefficients without thinking about integration by parts identities. And I mean, the first step is really to notice that we should really be thinking in cohomology. Feynman integrals are not unique. We can always shift them by a total derivative, or in physics language, an IV integration by part identity. So we should really be looking at the cohomology, which is closed form. So Feynman integrals are middle dimensional, so that's fine. And then we want to mod out by integration by parts identities. For free, this cohomology of Feynman integrals, we get a dual cohomology via Poincaré duality. And then we can pair forms in the dual space with forms from the Feynman integral space in a product called the intersection number, which is simply just the wedge of a dual form with a Feynman integral. And if we properly orthonormalize this, then we get this very nice quantum mechanics like decomposition of identity. So if I just use that on some random Feynman integral, I get some in terms of my basis Feynman integrals, and then some coefficients. So this is exactly the type of formula that we're interested in. This right here would be my C. And moreover, this intersection number, to actually go ahead and compute it, it's quite nice since it's algebraic. So it ends up just being a bunch of iterated residues. So taking all this into account, we feel like we're in the right direction to getting what we wanted. The question is, well, we know what the space of Feynman integrals is. So what is this dual space? And there is a sort of unsatisfactory answer. It turns out that there's a this dual space is well known in the math literature for a deformed problem. That is, and the deformed problem is when all the propagators have generic indices or generic powers. So essentially, we have to deform our Feynman integrals, take all of these propagators that are poles, and change them into branch points. So we add this power epsilon times alpha for alpha generic. And this does work, but it's sort of missing the spirit of generalized unitarity in the sense that, you know, this transition from propagator poles to branch points obscures connection to generalized unitarity cuts, and this is exactly what we want to improve on. Okay, so let me just go ahead and give you the answer for what this dual space looks like. So essentially, the dual form, any sort of a dual form is going to be localized to a generalized unitary cut. So on the one side, we have these Feynman integrals, which have propagators or poles. On the dual side, these poles, we need to have either boundaries or zeros at these poles, where the particles are going on shell. And in fact, we actually have to have the stronger constraint that there's we actually have to have compact support on these boundaries. So essentially, the dual cohomology is spanned by holomorphic forms times either a step function, which has support away from these cuts, or a d theta. And this d theta, you know, it's roughly a delta function. So this is going to take a residue when we put this in the intersection number. So and every dual form, it needs to have either a theta or a d theta for every propagator and every branch point in order to have proper compact support. I just want to give sort of an intuitive feel for what these dual forms look like. The first thing to note is that in this sort of the d-dimensional or the 4 minus 2 epsilon dimensional integration measure is actually so our forms are actually 5 forms, and essentially it's because we have this physical 4-dimensional loop momentum space. But then we also have this epsilon dimensional space, which is perpendicular to this space. And after we do the angular integration, we're still left with a radius. So we have this dl perp squared floating around, and this angular integration also gives this universal multi-valued function. And this thing is what's known as the twist. And essentially, we're going to want to work with single-valued forms. So if I have any integral that goes like phi, where this phi is single valued, and I take a derivative of this, it's the same thing as epsilon, turning this into a covariant derivative where so we're really going to be thinking about the cohomology with respect to this covariant derivative. And sort of pictorially, the structure of these dual forms looks something like this, where we can either have a phi form on a 0 cut, but it turns out that space is empty. Or we can have 4 forms on the 1 cut, or all the way down to 5 forms localized to a 5 cut. So this guy is extremely simple. It's got 5 of these d thetas, completely localizes the intersection number. It's just the residues around these propagators. This guy is slightly more complicated because the propagators, the d thetas that are localizing all these propagators, only fix 4 of our variables. There's still 1 left over. Essentially, the way that we just need to make sure that whatever's left over has compact support with respect to where these branch points are, which is given by where this radius goes to 0 or infinity, and then we can stick that into our intersection calculation, and I'll say a bit more about that later. But so essentially, now if I want to extract the box coefficient in this language, I can just take any Feynman integral, put it on the right hand side here, and then I put in this dual form, this box dual form, which again it has these 4 d thetas localizing to the quad cut, and then it's got this leftover piece, which will contain some additional d thetas localizing onto where the branch cuts are. But okay, so first these d thetas from these propagators, they allow us to just take the residue on the box cut. So that just moves over to the right hand side, hits whatever's there, this integral, and that's actually going to factorize this integral, and then we can get this from gluing together cuts. And then we have this leftover piece, and that's just another calculation that we can finish off. And once we're done, we're left with a rational function of Mandelstam variables and epsilon. sort of bird's eye view of how all of this works is that we need to start by choosing a dual basis of basis of dual forms, and we would like to do it in a certain way. We would like so once we choose this dual basis, we have to compute the differential equation satisfied by these dual forms. And if that differential equation is something that we call uniform transcendental, then we can continue. If it's not, we have to go adjust our ansatz, our basis, and tell it is UT. Just by choosing our basis and requiring that the pairing with the basis of Feynman integrals is orthonormal, the basis of Feynman integrals is actually completely fixed by our choice of dual basis. So we never actually have to reference it again, especially since the differential equation satisfied by this basis of Feynman integrals is exactly the same as the differential equation here for the dual forms, except minus transpose. So once we know the differential equation for the dual forms, we know the differential equation for the Feynman integrals, and we can just go ahead and integrate, and then we just get our integrals. And we can use that to compute loop amplitudes. The second thing we need is the C map. So you need to make sure that whatever dual form we're writing down has the right compact support. And once we do that, then we compare one of our dual forms with any Feynman integral in the intersection pairing, and we get out a generalized unitarity coefficient. And then, of course, we compare these two guys here to reconstruct loop amplitudes. Okay, so this is a good time to stop and ask if anybody has any questions about.
I have a simple question.
Yeah, go for it.
So you're working in 4 plus 2 epsilon, but does this work also when epsilon is negative and equal to, 2 epsilon is minus 1? Equal 3, is there something special or?
Well, yeah, there's nothing special whether I change 4 to 3 or 2 or 1 or anything like that. Though if I want to work in, if I want my integrals to still be regulated, I still need to have this epsilon parameter around that's generic, that's regulating everything. If not, then I'd have to consider this this strictly 4-dimensional cohomology, and that's actually turns out to be it's a little more complicated, actually. I don't know. Does that help or?
Yes and no, in a sense that yes, you're saying it's very general, but at the end of the day, can you take the limit when 2 epsilon is minus 1 and get your final expansion 3D instead of doing
yes at the very end? Because yeah, at the very end, as long as you've got the answer to all orders in epsilon, then you can take epsilon to whatever.
Mm-hmm. So there's no like even odd structure in the mathematics that's in this dual cohomology that you see, because there's often like even odd effect.
Yeah. No, that's a good question. There might be. I don't know actually. We've stuck mostly to even dimensions, but
40. Yeah. Okay. Thanks. And then John.
Okay, I don't want to interrupt the flow, but this graph is kind of abstract, and you say, well, you have differential equations satisfied by Feynman integrals. Could you write down a concrete example of that?
Yeah, sure. A very simple example would be a tadpole integral. So if I do d by dm squared, and you do integration by parts, and then this will be some number times my original integral.
And what is the number? And where's epsilon?
So epsilon's hidden in this d. This number, it should be, I mean, I think
d is 4 plus epsilon.
Yeah, I mean, this should be like m squared to some power, essentially.
So these are just linear homogeneous differential equations?
Yeah, it's like a Gauss-Menon system.
Gauss-Menon, you said?
And I'm saying it wrong, I'm sure. But the whole point is that if I have some integral, vector of integrals, it's...
Gauss-Menon, you mean?
Yes, that's what I mean. Yes, sorry.
Oh, that's...
I haven't had to say that out loud very often, so...
Oh, okay. Gauss-Menon.
Sorry.
So these are... oh, okay. It's like Picard-Fuchs equations. So it's for cycles. The Gauss-Menon equations are, yeah, they're for elements of the cohomology class, I guess. And they're linear differential equations. Can you give a more complicated one, let's say for the box diagram?
Yeah, so actually, okay, yes, I do know the box off the top of my head. So if I have going to be epsilon up front.
Would you mind writing down the box integral?
Oh, yeah, sure. Sure. It's getting a little squished. So it's four propagators. L squared, L plus P1 squared, L plus P1 plus P2 squared, all the way to.
These are Euclidean or Lorentzian?
This will be all Euclidean. I've done a Wick rotation already. The structure is going to look like this, roughly. And there's going to be S's and T's. Like, I just don't remember if it's S over T, T over S, or.
And the operator on the left is what? Is it Laplacian or something?
This guy, yeah. So this was
with
this
respect to the
covariant derivative. Yeah, with respect to the to the momentum here, or the Mantle stamps. But essentially, it comes from this guy is d plus omega wedge. Omega is d log of this this twist. And once we restrict this twist to some cut, it's going to gain some kinematic dependence, and this d will hit that kinematic dependence, and I can write it as, you know, d like internal loop kind of guy plus a kin. And when I say kin, I'm just talking about this piece of it.
So Gauss-Vannin integrals are, I guess they're not really integrals. They're just cohomology classes.
Yeah, they're just differential forms.
They're usually with respect to some kind of an algebraic variety surface or something. So
yes, that is right. I haven't said anything about the details of that so far. The way this talk is structured is we're going to take very seriously the idea that the cohomology dual to finite integrals should be a compactly supported cohomology.
So I think usually one works in a slightly different, like at least in mathematics, one works a slightly different way where, yeah, so there's some manifold X where the finite integrals are living, and there's another one X dual where these dual form stuff. And, you know, it's going to be like something like, you know, C5 minus where these propagators equal 0, or where this is going to 0 or infinity. And yeah, we're saying that these dual forms are living in some compact cohomology with respect to this and the kinematic and the connection there. And yeah, I think usually one would start with some algebraic cohomology, and then they would pass from this algebraic to this compact support using a CMAP and or some sort of isomorphism. And you have to be careful that this yeah, in degenerate cases you might have to do blow-ups and stuff in this case to correctly reproduce what you need over here. This is my understanding of it, and in some sense we're avoiding this and just trying to work this as much as possible directly with this guy here.
So the differential equations are all Gauss-Vannin equations.
That's right, yeah.
And and each Feynman diagram has some kind of algebraic variety associated with it. I mean, my understanding of the Gauss-Vannin equation is you take a basis for the cohomology, a finite set of generators, and so when you deform the surface or whatever dimension of the variety is, you are always in a finite dimensional space. So when you take these derivatives, you're going to end up with some sort of linear relations between them, and that is the Gauss-Vannin equation. Am I right?
Yeah, yeah, that sounds right. And I'd say that we're definitely in that situation.
Okay, so there must be some surface or some higher dimensional algebraic variety associated to each of the Feynman integrals.
Yeah, probably. I'm not going to claim I'm a super expert on algebraic geometries. So, but yeah, we definitely know. We usually think about it as a, like, I usually think about it as some manifold. It's essentially C5 minus some stuff, or, you know, C5 with some points removed. So in the end, the manifold is non-compact, and that's why we have to think about making our dual forms compact.
Mm-hmm. Okay, thanks very much.
Yeah, so let me sort of try to describe what these dual forms look like for one loop integrals. And at least at one loop, the geometry is quite simple. the bulk homology, where there's nothing localized to any of these boundaries, is actually empty. And so any non-trivial cohomology class has to have at least one cut propagator. And at higher loops, this leads to the slogan that no loop is uncut. And for one loop integrals, the twist is always something really simple. It's a sphere. So essentially, as soon as I solve one of these propagator equations, I'm fixing L perp squared to be some quadratic in the other variables. We're essentially looking at the space C4 minus this sphere with some radius. And after we do this, all of the other propagators are actually linearized. So subsequent cutting doesn't change the geometry, since the intersection of a sphere and a hyperplane is still a sphere. So we just need to look for a basis on all of these various SNs. And it turns out that each one of these has a single generator. It's just the volume form on the cut. We're going to normalize it by radius. It's convenient for the differential equations. And then our only freedom after that is really to just fix this power that we're dividing by this sphere. And so we have one of these forms exist whenever the radius is not zero or infinity. And essentially we can just construct our basis by just counting all of these possibilities, and it turns out that we won't overcount. So we can overcount in some degenerate situations, but we definitely won't miss any. And so in the very generic situation of where we have all different masses, there are 5 tadpoles, 10 bubbles, 10 triangles, 5 boxes, and a pentagon. And they all look roughly the same. They have various numbers of d thetas, which are telling us that we're localizing to various different generalized unitarity cuts. And then they have some more theta functions enforcing this compact support. And then it's just some simple sphere form where the powers have been chosen such that we get a nice differential equation that is proportional to epsilon. In the sort of, we'll mostly stick to this massless case where there are just 5 bubbles, 5 boxes, and so as I was saying, this choice actually has a nice differential equation. It's what we would call a uniform transcendental, in the sense that well, first it's canonical in the sense that it's strictly proportional to epsilon, so I can integrate as a series in epsilon, and then each one of these terms has a fixed transcendental weight, and this matrix is just a matrix value 1 form with dependent only on the kinematics. And yeah, so when we normalize our forms and dual forms such that we have an orthonormal pairing here, then the kinematic connection for Feynman integrals is just the minus transpose of the kinematic connection for the dual forms. Okay, so this is how we will construct our integrals, which we will pair with the coefficients to get loop amplitudes. So just a quick note on why the dual differential equations are transposed, at least some intuition for why this happens. So normally, if I took a box and I took its derivative, I'm going to see that it's once I simplify it, it's going to have something proportional to itself, plus something proportional to a triangle, plus something proportional to a bubble. So it contains all of these lower, less complicated sub-topologies. On the dual side, however, when I'm going to do integration by parts, I'm going to eventually hit a derivative is going to hit this theta function, and that's going to localize what's already a form on a 2 cut to something on a 3 cut. So that's the sense in which these differential equations are transposed.
So you said theta function. What I thought the theta was some kind of 1 form, but what sort of theta function are you thinking of?
A heaviside step theta, essentially.
A one-dimensional function.
Yeah, it's one-dimensional. I mean, yeah, you could use a bump function if you wanted, but we find that a theta is good enough.
When you say heaviside, is it that you're somehow replacing something complex by something real, or what? I mean, the usual the elliptic theta function would involve imaginary exponents. So What do you mean by the heavy side theta function?
It's just a step function, John.
It's just the solution to the heat equation.
No. So
Derivative is delta
you're thinking of
function.
Jacobi's theta function. This is just like theta of x.
Oh,
for real
theta.
x.
Oh, I'm so sorry. That's why
It's just.
Oh, I'm sorry. Okay.
Yeah.
Okay. I was off.
More simpler than the ones you're referring to.
Yeah.
Okay, sorry. Just a step function. Okay.
It's just a step function, and we're just doing this to sort of brutally impose compact support.
Okay.
And it yeah. I mean all of this compact support stuff has an algebraic. Well, okay, never mind. Let me not say anything about that.
But I mean, is the aim? I just want to get a little perspective. Is the aim to avoid having to evaluate these loop integrals, and instead computing the amplitudes by the fact that they satisfy these differential equations or something like that?
That's part of it, yeah. So at one part we know we have a basis of integrals. So any amplitude that I'm handed, it must just be some linear combination of these guys here. So we need two things. We need to know what these integrals actually are, and that's the step with the differential equations. It turns out that it's much easier to just solve this differential equation order by order in epsilon than to directly integrate. So that's the step with the differential equation. And then the next step is, well, you know, if I'm given some very complicated diagram, you know, it has to be some of these has to be some linear combination of these integrals. So how do we compute these CIs? And we're going to do that by, and essentially we can do that by pairing the form that's dual to this Feynman basis Feynman integral with this very complicated monster. Does that sort of make sense?
Well, it makes sense, but I'm just not sure what the strategy is. You presumably don't want to have to evaluate these integrals.
I definitely don't want to evaluate this, but I have to evaluate these.
Okay.
And by evaluate, I mean I need to know them, and I definitely don't want to do direct integration, and that's why we think about differential equations instead.
That's what I was asking. Okay. Yeah. So that's the strategy.
Yeah. So
you're trying to get the loop amplitude without having to integrate, but you are doing it by solving differential equations.
Sure. Yeah. At least one step of it. Yeah.
And I mean, you never specified. You know, I guess these are scalars, or these scalar fields that are going around the loop?
Yeah. So it turns out. Well, okay. Yeah. I'm actually being so. Yeah. It doesn't matter actually. No matter what theory you're in, you can always do a reduction and express all of your integrals as scalar integrals. You know, where you can take the tensor structure and you can write it as a scalar integral times some tensor structure.
Okay, and that's true for massive, massive particles as well. I'm familiar with something like that when everything is massless, but you're saying this is true, that you can write a higher spin, Feynman diagram, and reduce it in terms of standard kinematic factors of the vertices and something which involves scalars, regardless of whether it's massive or massless.
I'm not an expert in that procedure, but yeah. Okay, so right, so yeah, we're getting these differential equations. There's a nice boundary sort of structure to this, that whether you start with an even or number of propagators, the recursion always stops after 3 boundaries. So the Feynman integral in its differential equation only ever talks to its codimension 1 or 2 boundaries. It's always going to terminate at this fourth guy in a complicated way for our odd number of propagators, but in a simpler way for even. I'll just skip the details there for time. So let me just give some details on this compact support stuff that I've been alluding to the whole time. So if I'm going to have a well-defined pairing between a form and another form, and yeah, and this Feynman integral, you know, it's living on this non-compact manifold. This, whatever's sitting here, this dual form has to have compact support in order to regulate any of the singularities of the Feynman integral. And it turns out that, you know, if you're given some phi here with either no compact support or partial compact support, we can construct this phi c such that their difference is a total derivative. So at least in 1D, this is very simple. We just need to find some local primitives in order to remove support around the singularities. So essentially, this phi c is just our original phi, and then we subtract, you know, d theta around where the propagators are going to 0 times some primitive minus d theta around some branch points, again another primitive. And these primitives, we don't have to know them exactly. We can compute them algebraically since it's just a series. We just need them as a Laurent series around these singularities. And yeah, so it's trivial for this one-dimensional case for one forms, but it gets a lot harder for when we're looking at say 3 forms or higher. And in practice, there's sort of 2 ways to go about doing this. One is fibration, and essentially the intuitive idea is just to sort of do one variable at a time until we run out of variables. And the upside is we get to reuse the simplicity of the one form CMAP. The downside is that we're going to now have a matrix or a vector value problem, and we have to construct the compactly supported versions of the entire basis of dual forms all at once. Another downside is that if I have some Feynman integral that started with a singularity at infinity, so it's got a double pole at infinity, as I start integrating over these fibers, the forms left on the basis are going to have higher and higher order singularities at infinity after each subsequent integration. And lastly, which is sort of a mixed bag, is that you would sort of think that we're computing some algebraic invariant thing. So you would think that choices shouldn't matter, but it turns out that in the end, you have to sort of like, you know, I don't know, break symmetry. I'm not quite sure how to say it, but you have to make choices. And these choices greatly affect the intermediate steps. So you can either make your life very hard or very easy. In the end, you'll get the same result, but we don't quite understand what are the good choices yet. There's another way, which is sort of combinatoric, and we sort of directly deal with the multivariate nature of the problem. And this allows us to construct the compactly supported versions of individual dual forms. The downside is we need to know primitives for every single way of approaching a singularity, and then we need to know primitives for those primitives, and so on. And so it's sort of mostly really only doable for 2 forms. And again, we have this problem of choice, and we don't really know what are the best choices to make, what are the best coordinates, what are the best primitives to use where.
So could you just say what is the meaning of the dimension of the matrix, and what are the indices labeling?
Yeah. So essentially, if I have some phi total, I need to break it up into some phi, say on one fiber, and this is a basis of them, and then I have to wedge this against some phi now on a base. So these I and j are keeping track of what I've chosen for a base as a basis on each of these different fibers. It's essentially just breaking up the problem so I can work one variable at a time. You know, so this guy will maybe contain the loop component L1, and this guy won't. This will be only L2, 3, L4, for example. And then I can perform the intersection number that I can perform the intersection on the fiber, and then I'm left with just now an intersection on the base after that.
So you're saying that the indices, you're talking about some sort of automorphism of the fiber, is that it? What do the matrices represent? You say that there are as many indices as basis elements for the fiber.
Yeah, that's right. Yeah.
So is the fiber, what is the fiber? Is it a variety, or is it a vector space, or what?
Right. Okay, so the fiber is going to be, yes, we're going to do this one variable at a time. So it's just going to be C. So it's going to be like, say, some component L1 in C, and we're gonna model it by some singularities here. And we're going to construct a basis phi I for the
I'm confused about your
one-dimensional cohomology.
I'm confused by your notation. You're using a backslash, and does that mean removing?
Yes, removing
singularity. That's not quotient.
Yes,
it's removing a singularity.
It's removing. Is that better? I'm not sure.
But then what is the? No, that's fine if that's what it means. But then what is the vibration?
Yeah. So essentially, we have one of these BCs sitting over top of. For every loop, we're essentially just doing one loop component at a time. That's it.
So the dimension is the number of loops, or
is it? No, it's the number of it's the number of it's the size of the loop, like the loop space. So we have say 4-dimensional loop momentum, right?
It's the dimension of the integral.
Yes, exactly. And we're just doing it one variable at a time.
Oh, I think I'm okay. Maybe I don't want to keep interrupting, but I'd really like to understand this. So, is it that the Gauss-Manin equation is of higher order as a scalar equation, and you're converting it to a first-order vector equation?
Well, I'm a little bit confused because at least we don't need to think about the Gauss-Manin connection at this point. It's really, we're trying to compute something like this, and the idea is to say, well, this guy. So what was so say this was a 4-form, this was a 4-form. What was the intersection of two 4-forms? And now we have a 3-form, a 3-form, and then we just do a 1-form, a 1-form, and we know how to do this. But now we have all these indices floating around. That's the price we've paid. Yeah, maybe we can chat about this after, and I can.
Yeah, please go ahead.
Yeah, so I just have almost done here. So the whole thing, what we're trying to do here is now actually construct loop amplitudes, and our test situation, well, or at least our test cases, our proof of concept, is to compute the 4-point and 5-point gluon amplitudes from their generalized unitarity cuts. So we already know that we can write these amplitudes as a linear combination of the following bases, and we just need to compute this intersection number, which, you know, it's some dual form localized to some cut, generalized unitarity cut. We move that over to the right-hand side. It becomes a residue operation. This factorizes whatever Feynman integral was sitting there, and so we can get whatever sits here after this residue's been taken just by gluing cuts. And then we have some leftover part which has to do with the branches and making sure that has compact support. Okay, so yeah, as I said, we've done a proof of concept. We've reproduced the 5- and 4-point gluon amplitudes at one loop. We have the generalized unitarity coefficients to all orders and epsilon. I'm not sure what to do with that, but that's okay. And I think the more interesting part of our study is actually we sort of systematically looked at the 4-dimensional limit of this formalism, where we have essentially we write what these epsilon dependent coefficients as, you know, we make their epsilon dependence explicit, and we look at these integrals and their expansion in epsilon. And we notice that we only need three coefficients here to describe the finite part of this 4-point amplitude. And each one of these coefficients is multiplying an independent function. So one of the things that we find a little confusing is that you know, when epsilon is not 0, we only need you know, 2 bubbles and a box to describe this function space or the cohomology. But as soon as we go to the strict epsilon to 0 limit, we actually need 3 coefficients for this bubble, 3 coefficients for this bubble, and 1 box. So that's actually 7. So it seems that there's a jump in dimension that we don't quite understand at the moment. But the sort of the interesting thing of this 4D limit is that we can find a compactly supported form for the bubble, just the bubble itself, and it looks roughly like this. It's a triple residue of some primitive times the S channel cut or the T channel cut, whatever it is, of the Feynman integral, and then from here we can isolate where each contribution in epsilon comes from, which residues contribute to which orders in epsilon. So, for example, this double pole in epsilon, it comes from the localizing to the triangle cut, and also one of the loop momentum becoming soft. So that's very physical and great, and then the 1 over epsilon term, it comes from where we localize to L perp squared equals 0, so essentially the 4-dimensional limit, but all the other loop momentum are going off to infinity. And the rational term gets a contribution from the loop momentum are always going to infinity. They can either go to infinity on the bubble cut or the triangle cut, but we get a contribution both from when L perp goes to 0 and when L perp goes to infinity. And this we find a little annoying because in 2008, Badger put out a paper where he was able to get these rational coefficients for one loop integrals, where he only needed to localize on this L perp to infinity thing. So here is another place where we think that the amount of choice in sort of what basis we choose, what coordinates we choose, greatly affects these intermediate steps, and perhaps we can make a better choice and actually in the future remove the need for the residue here. So that would be something for future work. Okay, so overall what we've done is we've recovered generalized unitarity in arbitrary dimensions from twisted relative cohomology. So we've done warm up at one loop. We found a uniform transcendental basis for dual forms. We obtained a differential equation for this basis in any dimensions, and then we constructed the one loop 4 and 5 point gluon amplitudes from the cuts, and we have the coefficients to all orders in epsilon. And lastly, we looked at 4-dimensional limits, and so essentially we're looking for these epsilon over epsilon terms when epsilon goes to 0. So the next goal is to extend this analysis to 2 loops, and we're working on that with another student at McGill in sort of a loop-by-loop fashion. And yeah, the other thing is improve the efficiency of this C-map. We really need to, I think we really need to understand a little bit better what are the right choices to make. And lastly, it would be nice to have a systematic way of extracting these rational terms at 2 loops. Thank you for your attention.
Thank you, Andrzej, for a very nice talk. Thanks, the speaker. And the talk is now open to more questions. All right, Rufus, please go ahead.
For the very nice talk. I just had a simple question. If you could possibly conceptually relate the way you're cutting these diagrams to like conventional Katkowski rules, is it similar to those?
Yeah, exactly. So it's the same thing. Exactly, it's the same thing, really.
It's sort of the additional
yes,
insight here into making these diagrams unitary, improving unitarity of the theory.
I haven't thought about that. How to use this to prove unitarity. If I had some 4D dual form and 4D Feynman integral, this would give me the 4D coefficient, and this is exactly the same as this sort of the normal procedure for say getting the box coefficient. And what's different in our prescription of how to compute this is we have this step where we're going to have some leftover piece, essentially box of the Feynman integral. So essentially what's different from normal generalized unitarity is we're really working I mean, you can also work with in d dimensions in generalized unitarity, but it's we get this intuition where we have these the same cuts, but we also get this epsilon dependent piece which comes, which is also there, which has to do with making sure things are compact support around the branch cuts, not the propagators.
Oh, okay, I see.
Yeah.
Would you mind defining what you mean by generalized unitarity?
Right. So generalized unitarity, the idea is essentially I have some Feynman integral, and I want to relate this to an ansatz of some rational term, and then essentially what we want to do is we want to take one of these propagators. You can think about either taking a residue at it, but usually in physics we just turn this into a delta function, and we integrate. And well, okay. Essentially, we want to match the discontinuities on both sides of this equation. Oh, maybe that's probably clear. But we're essentially just taking an ansatz and our integral, and we're just making sure that they both have the same discontinuities. And we're making sure that, and so we're fixing these coefficients so that they have the same discontinuities.
I guess I don't know intuitively what that means. Unitarity in usual scattering theory just means essentially conservation of probability. But you mean something at the level of each individual Feynman diagram.
Yeah, so I mean, okay, yeah, normally I guess you're familiar with the optical theorem,
of course,
and then we would take unitarity cuts, which you know you need to like cut two propagators to do a proper unitarity cut. So the idea of generalized unitarity is sort of saying, well, what happens if we also cut this?
So are you essentially just putting in the Flamel's formula into the Feynman integral? Is that what you mean by unitarity?
So is it replacing it with this kind of thing?
Well, it's essentially for an integral of the type 1 over x minus y, you write it as the principal part of 1 over x minus y plus a delta function.
Plus a delta function. Yeah, exactly. So we're essentially just taking the delta function part of that.
So maybe I can ask a quick question. So looking forward, is the hope that this method will be more efficient to obtain these coefficients for higher loops than what we currently have? Just because it's algebraic and much cleaner than doing these integration by parts. Is that
yes, that's the hope.
Is a hope? That's
the hope, or at least it should provide some like analytic understanding or intuition of why, you know, say I have a Feynman diagram, I put it into fire or something, it spits me out its decomposition in terms of some basis, and I notice that one basis element is absent, you know, and when you do integration by parts, you have no reason, you're kind of like, I have no idea why one of these coefficients was 0, whereas at least here you can kind of track why this coefficient was 0. It's because you know, the dual form is localizing something to a certain singularity, and the form itself just doesn't have enough singularities there to have a non-zero residue. So we can really understand things in more analytically like that. So at the very least, I hope it will just provide better analytic intuition. But yes, hopefully it would be.
Is there like
more
a
efficient
intuitive way of thinking about this dual forms, like physics-wise, like a real? Because mathematically, I understand the structure, but is there a way that you think about this more intuitively, or not yet?
Yeah, so I mean, I think all the intuition really comes from, I think, generalized unitarity cuts, and just like you know, people have been, you know, I don't know how long, maybe 10, 20 years, they've been able to somehow get these coefficients by just putting various combinations of propagators on shell. And there was sort of no deeper underlying mathematical reason for why you could do that in some sense, and I think this is what the reason why we can do that. So essentially doing what people have already done in generalized unitarity, they're basically doing what a dual form does. We've just sort of systematized that, and we systematize that in a way that allows us to get the epsilon corrections straightforwardly.
Okay. Yeah, no, I mean, it looks like a very promising program, and maybe we invite you in 5 years and you tell us the entire solution for any Feynman diagram.
Yeah, that'd be nice.
And on this note,
Yes.
do we have, I think we've bugged you with enough questions. So if I don't see any further questions, so, thanks again for coming over today via Zoom and speaking.
Thank you for having me.
And good luck with this cool program.